Hello, hi, good morning. So this is me Sanjay Pawar. So guys, I'll be teaching you mechanical metallurgy from George E. Dieter. The aim of this series is to help you understand mechanical metallurgy, which mostly aspirant find it difficult to read because it's very vast and some points are very complex. So let's begin. So starting from mechanical metallurgy, what do we do in mechanical metallurgy? We study response of metal to forces, importance of microstructure and their effects on mechanical properties, and the topic of failure analysis we also do. So before starting mechanical metallurgy, we need to consider some assumptions. Okay, so what are those? So the body should be continuous. What does that mean? It means that the body should not contain any void. No void means no material loss or no atom missing from the body. It's called the continuous. And second assumption is homogeneous. Homogeneous means property of the component at each point is same. That's called the homogeneous. And if we say isotropic means if you take a block of metal in all direction x, y and z, the property should be same. So now we see the stress. So what is stress? Stress is nothing but the internally resisting forces over a unit area. Here the internal resisting force F is represented or written as integral of stress times A. We know that the stress is internal resisting force per unit area, means force is stress is equal to stress, we can say, for 1. But in case when the area of the bar is A, it will be written as force stress times A, and stress can be written as force upon area. Strain, which is also called the fractional deformation. So let's take an example of when you have a bar of length L1, you applying force in the tensile direction. Okay, so final length is comes out to be L2. The change in length is going to be delta L, final length minus initial length L2 minus L1. So the change per unit original length is called the strain. It is also represented as E in case of the engineering strain. So now we will see elastic behavior. So initial length here is L1 when there is no force, but when force is applied, length becomes L2. So length has increased here, but when load is unloaded, length will come back to the original length, which is L3. So here what is happening? Initial length L1 and the final length L3 is equal. It is called the elastic behavior. Like any material will show elastic behavior only up to their elastic limit. We will see what is elastic limit later, and only up to the elastic limit Hooke's law is valid. So what Hooke's law says is that stress is proportional to strain, and here the proportionality constant is Young's modulus. So Young's modulus is also called the stiffness. But in case of the plastic behavior, material does not gain its original shape. Therefore, we also call it permanent deformation. So the term related to plastic deformation is yield strength, which is minimum amount of stress required to cause the plastic deformation. Here is a really good point that volume change is constant in case of plastic deformation, whereas volume change in elastic deformation is not constant. So therefore in plastic deformation we write volume in undeformed is equal to the volume deformed. So here the terms comes average stress and average strain. So whatever stress and strain we have discussed above are called the average stresses, because we assume that the stress distribution is same, there was same deformation at each point. So now we will see the stress strain curve for the ductile metal. Okay, so here first the point is proportional limit, after that elastic limit comes, A point, B point, and after that yield point comes, and at the top this point is called the UTS or the maximum tensile point. So after that, when the point at which the fracture happens is called the fracture point. And the curve shown on the left side is for steel, which shows upper yield point and lower yield point. and right side curve is for aluminum, or you can also call for the copper. But in case of the brittle material, the stress strain curve here is shown as a straight line. It does not show the peak point because this metal fractures at the elastic limit. There is no plastic deformation in case of the brittle material. So we need to know more about this E, Young's modulus. It is the stiffness of the material also, and it can be written as stress upon strain. What information can we get from the potential curve? So potential energy, which is our separation between the atoms. So greater the depth of this curve, the more the value of the stiffness is going to be. Okay, so tell me in which of the case the Young's modulus is going to be higher. So depth here is higher. Okay, so Young's modulus of curve B is going to be more than curve A. So now let's see what is maximum tensile strength. Maximum tensile strength, also called the UTS point, the point at which the necking start. We will see the what the necking is later. So here sigma UTS is written as maximum load upon the original length or the original cross section area. Always remember that in case of the engineering stress, we will take original cross sectional area. Working stress is nothing but the stress at which we have to operate the component without causing failure. For that reason, we take some safety factor which is called the safety factor. For the ductile metal, it is the ratio of yield strength and the safety factor, and in case of the brittle material, it is the ratio of maximum stress or the tensile strength to the safety factor. So now we see the shear stress. Shear stress is represented as tau, and always remember the unit of stress is megapascal. So tau is also written as this G times gamma. So here G is this shear modulus, just like the Young's modulus in case of the tensile stress. When there is shear stress, there will always be this kind of strain which is called the shear strain, denoted as gamma. So it is the ratio of angular separation upon the height. So instead of linear deformation, there is going to be the angular deformation. So this change in the dimension is a and height is h, and which is also written as tan theta. So now we will see how this gamma became tan theta. So we know that when initial shape was here, okay, after the angular separation, the theta angle was made. So this is the final curve. So we know that tan theta is nothing but the height upon base. So when the triangle is like that, so height over is a and the base is h. So therefore we are writing tan theta as a upon h. So that's it for this lesson. We'll see in the next lesson.